Hello, this is my Physics 2212 Lab 4. Alright, so introduction. Essentially, we're going to use Kirchhoff's circuit laws and Ohm's laws to predict the resistor and capacitor behavior in a real circuit. We're going to do this mostly by measuring currents and voltages in different places along the circuit. The system is the wires, resistors, bulbs, capacitors, and batteries. And then the surroundings is the universe. Kirchhoff's rule essentially states that the change in voltage across an entire circuit has to be equal to 0. Capacitors, it's just a basic delta V equals Q over C, when C equals epsilon naught M times area, or A over D, a distance between. And then Ohm's laws, delta V equals IR. The in-series capacitor rule, Req is equal to the sum of all R's, all of the resistors. And then in parallel, 1 over Req is equal to the sum of 1 over each resistor value. So the results of predicted values almost match the observed. And then current is time dependent in an RC circuit. Okay, so the first circuit I have here is listed to the right. Above is the picture we took. It's not very good. We only have one ammeter in there, but there's another one. And then there's 2 circuits. So, I mean, 2 capacitors and then 2 batteries here. Yeah, laser. Yeah, 2 batteries. And then there's one of our resistors. And I think the other one's off screen. So essentially for part 1 here, the circuit from the last slide is made, the currents are measured, the connection was then reversed and remeasured, the voltmeter readings are taken at different points by switching the first ammeter and then removing it from the circuit. Okay, so then for part 2 we're going to do, basically we're going to add a capacitor and a light bulb, remove the resistors, and measure essentially how long it takes a light bulb to charge, or how long it takes a light bulb to go out with a capacitor attached with the battery, and then remove the battery and see how long it takes for the light bulb to go out with just the capacitor. So you're basically charging and discharging the capacitor. Okay, the currents are both 20 milliamps, so like 0.20 amps on both. Basically all of these were all 0. So this is like the map here, you can see. And yeah, and then this is like the here, I get this to draw. This is like the graph. So basically from here it would go like down, and then it would flatten out here. That's like, imagine that's flat, and then this would go down more, all the way to 0, and then it would stay at about 0. So it's not quite 0 because there's a little distance from the wires and the ammeter, but this is like 2-ish. Okay. And then yeah, so basically if you change the ammeter to a voltmeter, the voltmeter has so much resistance, so it's just going to travel through the ammeter and not through the voltmeter. And so if you just keep the voltmeter where it is, like originally where it was in the first part of the circuit, it's gonna like cause a problem. It's just gonna like short circuit the circuit. Basically the whole circuit's just gonna stop working because there's no connection to the rest of it since it's such high resistance. When the ammeter is placed in parallel with the resistor, it just travels with the ammeter because it's essentially 0 resistance. And then the calculated R is using the data above for 47 and 101 ohms. Right. Results part 2. Basically, I already described the way it works here, but you ended up getting that it takes about 9 seconds for the battery to charge, and about 18 for the 2. But obviously these ID values are 10 and 20, so it's really close, but not quite. Okay. This was using the ln of delta V over delta V naught equation is equal to -2 over RC. You essentially plot this using the 30 ohm and 200 microfarad resistor or capacitor, and then get the RC value, which ends up being 6 seconds, which is as expected. So some sources of error include basic human error in timing the discharge and recharge. And slight resistance from the wires and ammeter also cause slight deviations from the ideal values, of course. And then what if part 1 was simulated? All values would be exactly ideal, as the ammeter and wires would have no resistance. And what if the charging of the bulbs was simulated? The bulbs would have charged ideally, while in real life it was slightly slower. And the ideal values were about 10 seconds for the 10 ohm, 20 for the 20 ohm. That's all.